In this video, you will learn about exponential functions, and then we'll talk through an example of exponential growth. An exponential function with base a is a function that changes by constant multiples of a. So this is a little bit different than a linear function where they changed by a constant rate, a constant slope. Here's what a formula for an exponential function with base a looks like. So we have some number p times a to the exponent t, and in this function t is our variable. We've chosen t because in most of the examples t is going to be time. Our variable will be time. Here's a few more details about p and a. The number p in the front is usually known as the initial value of the exponential function because when we plug in 0, meaning we put 0 in the exponent of a to the 0 becomes 1, and p times 1 is just p. So when we plug 0 into our function is equal to p. That's why it's called the initial value. And make sure you're paying attention to where the variable t shows up. It's in the exponent of the base a. Another thing that you should keep in mind going forward is that the base a is also known as the growth rate or decay rate, depending on the context. Now let's talk through an example of exponential growth. Suppose that during an epidemic, the number of cases of a particular disease doubles every week. There were 5 cases of the disease on the first day of the epidemic. So given this information, we want to calculate the number of cases over the first several weeks. So I've made a table. In my left column, I have the number of weeks that have gone by, and in the right column, I've written the number of cases of the disease. So our starting point is week 0, and we started with 5 cases. So this is our initial value. After 1 week, the number of cases will double. So we take the value 5 that we started with, multiply by 2 to get 10 cases. And then we just continue that process. After another week, on week 2, the number of cases doubles again. So we multiply 10 by 2. And I've pointed out here that 10 is 5 times 2, and we're multiplying by 2 again. So we're actually multiplying 5 by 2 squared. But either way you think about it, 10 times 2 or 5 times 2 times 2, we get 20. Let's go through these a little bit quicker. After 3 weeks, we multiply by 2 again, and keeping track of the number of 2's, we get an extra one, so that's 5 times 2 to the 3rd power. We get 40. Multiply by 2 again as we go into the 4th week. 40 times 2 is 80, and now we're up to 4 2's here in our multiplication. And here's weeks 5 and 6. We multiply by 2 again in week 5 to get 160. We're up to 5 2's. And in week 6, we multiply by 2 again to get 320, and we're up to 6 2's in our multiplication. So here's what's going on. To get the number of cases after t weeks, what we actually need to do is multiply the initial amount, 5 in this case, by 2 to the t power. So looking up here, after 5 weeks we have 5 times 2 to the 5, 2 to the 5th power. In week 6, we have 5 times 2 to the 6th power, and so on. So the formula for our function looks like this. The number of cases after t weeks is equal to 5 times 2 to the t power. Let's take a look at the graph of our exponential growth function before we move on to exponential decay. I've already entered the data from our table here. I have weeks in our first column and the number of cases in the second column. And on the graph, they've been plotted in with green points. I've also adjusted my graph settings so that we can see the data. My x-axis goes from -2 up to 8. My y-axis goes from -20 up to 500. So this lets us see everything that's going on. Now I want to plot in the line for the number of cases, or I should say the curve for the number of cases. This is 5 times 2 to the t power. So now the exponential function has been plotted in as a black line, and we can see the curve. So notice how this is very different from a line, which would look flat. Here it's curving upwards, and we can see it starts curving upwards quite steeply.